Hello everyone. Today we'll be talking about various separation techniques that are tested at the ordinary levels chemistry. Just remember that these techniques are totally physical. They employ physical processes like boiling, like condensation. Okay, they are used to separate one component from another that is only physically connected. It does not involve any chemical change at all. So we'll be talking about filtration first, whose principle is very simple. This is how you actually make tea at home. For example, let's suppose you have cooked a pot of tea for yourself and now you want to drink it. What will you do? You will pass that tea through the stainer. The stainer acts as a filter medium, which in this case is the filter paper. Let's say this is a mixture of tea and tea leaves that you just cooked. Tea and tea leaves. Tea leaves are the insoluble component and tea itself is the soluble component. So you will pour the mixture through a filter medium, which in this case is filter paper, but at home you use a stainer. So the holes of the filter paper are smaller than the tea leaves, which makes them to suspend on the surface of the filter paper, and they are called residue. The insoluble component that stays on the top of the filter medium is called residue, and the soluble component that passes through the filter media, which in this case is the filter paper, that is called filtrate. So remember, filtration is a technique that is used to separate insoluble solids. Okay, let's talk about vaporization now. Again, vaporization is pretty simple. This is the experiment that you can even do at home. Let's say I have a soluble I want to separate a soluble component from a solution. Let's say I have salt and water. Let's say this is a mixture of salt and water, and I want to separate salt from water. We know that salt is soluble in water, so obviously we cannot use filtration. So what will you do? You'll heat it. When you heat it, water will start to boil at 100 degrees Celsius, and there will come a time when all the water will be evaporating and you will be left with salt. You can even do this experiment at home. Like I said before, you can simply take a pot of water and you add some salt into it and then evaporate and actually boil all of the water, and you'll see salt deposits on the pot. So the other figure, this figure is different from the first figure. This is a figure for evaporation. This is a figure for evaporation. This is vaporization. Many students confuse one with the other, but the truth of the matter is vaporization is different from evaporation, and evaporation is similarly different from vaporization. The difference is that vaporization happens only at boiling points. Vaporization happens only at boiling point, and evaporation happens at all temperatures. Evaporation happens at all temperatures. Evaporation basically explains a very simple phenomena that when it rains, we see puddles of water. Even at night, we see puddles of water. And the next day, by evening, we see that puddles are no longer there. Where does that water go? Obviously, our municipalities are not that active to remove that water from the puddle. So obviously, it is being removed with the help of a natural phenomena, and that is evaporation. So obviously, it is not 100 degrees Celsius outside. It can't be boiling. So it is actually the evidence. It provides the evidence for evaporation that it happens at all temperatures. That even at, let's say, 25 degrees Celsius, some molecules in a puddle of water, some molecules of water will always have energy to leave the surface of the liquid. So that's how those puddles, decrease in volume, and there comes a time then that there is no water remaining in a particular puddle. So this is the difference between evaporation and vaporization. So moving on to crystallization. Crystallization is a technique that is used to separate a soluble salt. It is used to separate a soluble salt by cooling its saturated solution. So first we need to know what saturated solution is. So before understanding crystallization, we need to first understand the concept of saturation point or saturated solution. So let's take a glass of water. Okay, let's take a glass of water. That is a pathetic looking glass, but you get the idea. So that I took a glass of water and I added some salt in it. That salt will get dissolved in water. Then I added some more salt. It also got dissolved in water. Then I added some more. There will come a point when no more salt will dissolve in water. That point is called saturation point. We can say at this point, saturated solution of salt and water is formed. Okay, so the first step of crystallization is that you dissolve the impure solid in a solvent such that a saturated solution is made. After that, you heat the solution to evaporate most of the solvent. Since solvent reduces in volume, so the solute itself, which was already saturated in this much volume, so when the volume of the solvent is reduced by evaporation, the solute does not have room to accommodate itself inside the solvent. So what will happen? It will start to come out, and when you leave it at room temperature or you allow it to cool down, the solid appears as pure crystals. Those crystals are then separated by filtration and then they can be dried. So that is crystallization. Moving on to decanting. Decanting is again very commonsensical. We do it without even realizing that we are doing decanting. Decanting is used to separate insoluble solids. Again, let's take the example of sand and water. And I want to separate sand from water. So what will I do? I'll take a beaker in which there is sand and water solution, and then I'll pour water from that beaker, let's call that beaker A, into another beaker, that is B, such that no sand particle gets poured with water. Obviously, it is not going to be 100% effective. Separation would not be 100%, but it gets the job done to some extent. So the crux, the heart of this chapter, that is distillation, and it is tested very frequently in exams. First, we need to understand the basic principle of distillation. Distillation is a process, it's a technique which is used to separate soluble liquids on the basis of the difference in their boiling points. For example, if I have two liquids, liquid A and liquid B, let me complete this. Let's say I have two liquids A and liquid B. The boiling point of liquid A was 50 degrees Celsius. The boiling point of liquid B is 100 degrees Celsius. So what will I do? I'll heat the solution. I'll heat the mixture. So A is going to evaporate first. So what will I do? I'll collect A. Okay, at 50 degrees Celsius, A will be evaporated and I'll collect A, and then I'll condense A and eventually collect it. So automatically A gets separated from B because A's boiling point was different than B, or we can say B got separated from A because the boiling point of B was different from A. Now, there are two types of distillation, simple and fractional. There is only a minor difference, but the basic principle remains intact for both types of distillation. Let's label this diagram first. So this is distillation flask or round bottom. It's basically a round bottom flask, but we are calling it distillation flask because it is being used in distillation. Okay, and this is a Liebig condenser, or a Liebig condenser. That's a thermometer that is used to measure temperature, that we studied in last class. And this is the receiving flask. So what exactly is happening over here? Let's say I have a mixture of salt and water. But in this case, I want to separate water from salt. Remember, in vaporization, we were separating salt from water. In this case, we are separating water from salt. What will I do? I'll heat the mixture. I placed it on an electric heater, an electric bath. So at 100 degrees Celsius, when the temperature reads 100 degrees Celsius, when the thermometer reads 100 degrees Celsius, water gets evaporated and it will enter the condenser. Once it enters the condenser, this water will be in the form of vapors, obviously. It enters inside these tubes. Let me just zoom in for you. It enters in these tubes in the form of vapors. So now we are going to condense these water vapors. And how do we condense it? Condensation is basically conversion of vapors into liquids. And how do we achieve that? By cooling. Okay, and how are we going to cool it? We are going to cool it with the help of some cold water. So cold water will go, cold water in, and cold water out, Okay, so the cold water will move around the jacket around the tube. It will move in the jacket around the tube. It will not come into direct contact with the water vapors that are coming from the distillation flask. It will only move around the tube inside the jacket. It will cool down the tube, which in turn cools the water vapors, and they will be condensed and collected in the receiving flask. Just remember, we'll always keep the receiving flask open. Why? So that if in any case vapor happens to enter this receiving flask, the pressure can build up. And if it is a closed system, that pressure can result into the rupture of this receiving flask. Okay, so this was the principle of, or this was the working of a simple distillation column. If they ask you, for example, let's talk in terms of what they ask you. Let's say they ask you to how salt water is purified by simple distillation. Okay, or they will ask you how salt water can be purified, or water can be separated from salt water. What will you do? It can be a 3-mark question. It is mostly a 3-mark question. So the first point will be heat the solution to distill it. We get 1 mark. Second mark, both the components, which in this case is salt and water. Salt can be NaCl mostly. Okay? Salt and water, both the components have different boiling points. And the one with lower boiling point, in this case is water, will evaporate first. Okay, and that water vapors will be condensed. Sorry, there's not a lot of space here. Water vapors will be condensed in a condenser. In a condenser, it will be condensed and collected. Okay, That's how you get 3 marks. Moving on to fractional distillation. There is a small difference between a simple distillation apparatus and a fractional distillation apparatus, and that difference is the insertion of a fractionating column in fractional distillation apparatus. So, what is it for? Fractional distillation is particularly used for mixtures. It is used for mixtures where components have very close boiling points. Where components have very close boiling points. So that's where the function of fractionating column comes into play. So how does it work? Let's discuss that. Let's say I have a mixture of two things which are x and y. Let's say the boiling point of x was 80 degrees Celsius and the boiling point of y was 100 degrees Celsius. Okay. So obviously x is going to evaporate first. If I start heating it, x at 80 degrees Celsius, when this thermometer, the bulb of the thermometer reads 80 degrees Celsius, the component x will start to evaporate. But the boiling points are not very different. So at 80 degrees Celsius, x have the energy, the molecules of x will have the energy to go up and enter the condenser. Okay. But obviously, why the molecules of y do not have enough energy to go into the condenser by themselves. But what they do is at 80 degrees Celsius, they have enough energy to mount on the molecules of x and start moving with them. So that's why we insert a fractionating column in which there are what we call some obstacles. In this case, is glass beads. They are used to hinder the movement of molecules such that the molecules which do not have enough energy get back into the boiling flask or distillation flask. So what will happen? Like I said, at 80 degrees Celsius, the molecules of X will start moving, but at 80 degrees Celsius, Y molecules will also have enough energy to mount on the molecules of X, and they'll start moving with the help of the energies of X molecules. So once they enter the fractionating column, these beads, these glass beads or glass obstacles, they are glass beads which are acting as obstacles. They are going to stop the movement of these X molecules which also have Y molecules mounted on them. X molecules have enough energy to navigate around these glass obstacles, these glass beads, and enter into the condenser. But Y obviously do not have that. Right? So when X, let's say if there is an X molecule and there is a Y molecule mounted on it, when they start moving, let's say they have to navigate from this glass bead and then this glass bead and then this glass bead. So X can move from here to here, but Y do not have enough energy to keep a strong hold on the X. So what will happen? Once it strikes one of these glass beads, the X molecules will still go up and into the condenser, but Y molecule will not have enough energy to keep up with the navigation, with this complicated navigation, and it will fall down. It will fall back into the distillation flask, and X will be separated. X will go into the condenser where it will be separated, and Y will remain in the distillation flask. Had we used the apparatus that we use in simple distillation without fractionating column, this Y molecule would have been able to move with the X molecule and enter into the receiving flask. So the whole point of simple distillation, the whole point of distillation or separation of components become moot in this case. So that's why we use fractional distillation for components whose boiling points are actually very close, and for components whose boiling points are very far, we can use simple distillation. Hope you got it. Moving on to the main application of fractional distillation which is fractional distillation of crude oil. Fractional distillation of crude oil. What is crude oil? Crude oil is the oil that Pakistan would love to have. Oil rich countries are which countries? The Arab countries. So crude oil is basically the oil that is extracted from the oil wells. It is called crude because it is crude, it is unfiltered, unprocessed. We process it to get various valuable hydrocarbons. So how do we do that? So crude oil have multiple fractions. They have like many components. They have many components who have different boiling points. They have different boiling points. Let's say A, B, C, D. Okay, and E and F. They are different components in the crude oil. So how does it work? We enter the crude oil, we feed the crude oil inside the fractionating column where it will be heated. Okay, and all the components will be separated on the basis of their boiling point. The component with the lowest boiling point will evaporate first and will exit from the top of the fractionating column. Okay, so let's say if we talk about gasoline, naphtha, kerosene, and A, let's say A, B, C, D, E and F. Okay, so A will have the lowest boiling point. That's why it got evaporated from the highest. That's why it got exited from the highest point. B had the higher boiling point as compared to A, but B had higher boiling point as compared to A, but lower as compared to C. And the highest boiling point will be of F. Lowest boiling point will be of A, then B, then C, then D, then E. We can also say A will be the lightest and F will be the heaviest. B is heavier than A, C is heavier than B, D is heavier than C. What does it mean by heavier? It means it will have more mass. Now let's talk about fractional distillation of air. Fractional distillation of air. We know air is a mixture of gases. So how are we going to distill it? Now that is a conundrum. How are we going to distill it? Obviously we are going to convert it into a liquid, because distillation happens we can only distill liquids, because distillation is about boiling points, about heating liquids. So obviously we cannot use air directly, but what we can do is we can liquefy air. So what are we going to do? We are going to convert air into liquid form. And how are we going to do it? We are converting gas into liquid, so we are going to cool it, and it's going to be extreme cooling. Okay, because if we see, let's say, that's written over here. So liquefied air gets liquefied at minus 200 degrees Celsius. As we know that air has different gases, so all of them have different condensation points. The lowest condensation point, I guess, is of nitrogen is minus 193 or 194 degrees Celsius. Okay, so liquefied air enters the fractionating column, and obviously the gases get separated on the basis of the difference in their boiling points. The one that is going from the top will have the lowest boiling point. Okay. By the way, we're talking about fractional distillation. If they ask you to describe fractional distillation of crude oil, you can use these same points, but you just need to add another little detail, that heat the solution to distill it in a fractionating column. Just introduce fractionating column. If you are doing fractional distillation of something, then you can say, instead of both the components, you can improvise, you can adapt as according to the example. If we are talking about crude oil, then you will have to talk about the components of the crude oil, but the basic template of the answer should remain the same. Okay, so moving on to paper chromatography. Paper chromatography is basically used to separate colored substances. It's just used to separate colored substances, colored substances on the basis of the difference of the difference in their solubilities. In their solubilities. Okay. So how do we do it? Okay. Let's take the example of this diagram. Let's take this diagram as okay. Yes, that will be fine. Yes, that will be fine. Let's say this is a piece of filter paper. Okay, I drew a line here that's called an origin line. That's called an origin line. Okay, this is made of. This is we usually draw it with pencil. The line itself. Okay. Then we add a spot over here. Let's say you want to see how. Let's say you want to see if you have a board marker, a marker, black marker. If you want to see which dyes are making or which colored substances are making this marker black, so you can just do it. You can do what? You can draw a line with a pencil and you can put the spot over here and dip this filter paper inside a solvent, such that this origin line, remember, it must be above the level of solvent. It must be above the level of solvent. Must be above the level of solvent. Why? Because if you dip it inside the spot, you cannot see the separation. You can never see the separation over here. Okay, so what will happen? Once you dip it, this solvent will try to climb up. By capillary action, you would already know that if you dip a paper inside a glass full of water, you will see that water climbing up the level itself, because it has that climbing ability that we call capillary action. So let's say this solvent is alcohol or water. We can take water, you can take alcohol. You can actually do this experiment at home. You can dip the filter paper inside water. This water will climb up and it will pass through this spot, the spot of dye, or like I quoted the example, the spot of a marker. Okay, once it passes through the spot, different dyes start to get separated. For example, let's say this spot was made up of three dyes, A, B and C. Let's say this spot was made up of three colored substances, A, B and C. Once the water passes through the spot, it comes into contact with all of these three substances. Now the solubilities are going to be tested. Let's say that A is most soluble in water. Let's say A is most soluble in water and C is least soluble in water. What would happen? Since the spot has three colored substances, so there are going to be three spots of these three substances. Let's say there are three spots. Just ignore the other things like these RF values and stuff. Just understand what's going on here. Okay, since A is most soluble in water, so it is going to travel most with water. What is the maximum that water traveled? This much. That is called the solvent front, or you can say final solvent position. Final solvent position. Solvent is water in this case. Okay, the spot that travels most with water is the spot of the substance that is most soluble in water. The spot that travels the most with water is the spot that is most soluble in water. So this is going to be A, and the spot that least travels with water, it is going to be the spot, it's going to be the substance that is least soluble in water. So this would be C and this would be B. So that's how they are separated. Okay, now you need to also understand what is an RF value. RF value is also known as retention factor, actually retention factor. RF value is actually an indicator of how soluble a dye is inside a solvent, or it actually tells you how much distance a dye is going to travel. So it is equal to distance traveled by the component or the dye or the colored substance over distance traveled by the solvent. They ask you to calculate it. Let's say I want to calculate the RF value of A. RF value of A. So how much distance did it travel? The distance traveled by A was this much. You will measure the difference from the origin line to the final position of the dye there. So A over distance traveled by solvent, that was again from the origin line. Do not take it from here. Do not take it from here. While measuring, do not take it from here. Okay, you'll have to measure both the values from the origin line. Okay, the distance traveled by solvent would be this much, A over B. So that's how you calculate it. Okay, also you can also estimate it, by the way. Let's say if he asks you that, if he tells you that the diagram is not drawn to scale, so in that case you cannot use a scale. Okay, but he can ask you to predict it. Okay, yes, you can predict it, because the value of the denominator here is always going to be greater than the value of the numerator, which means that this fraction will always be less than 1. Will always be less than 1. Okay, let's say if the solvent traveled distance equal to 2, so we know the component will always travel the distance less than 2, let's say 1.5 or maximum 1.9, but still value will be less than 1, less than 0, less than 0. Okay, so let's say if there is a spot right at the center, what would be its RF value? The spot at the center means you can actually predict it. If you give a random value to the solvent, let's say that the solvent traveled 5, or you can take 4, or you can take 3. Okay, and we know that the spot traveled exactly half. So you can actually estimate the value from it. So if 5 is the distance traveled by solvent, 2.5 is the distance traveled by dye. If 4 is the distance traveled by solvent, 2 will be the distance traveled by dye. In both the cases, the answer would be 0.5. In this case, 1.5 and 0.5. So the value will always be less than 1. Always be less than 1. Okay, it will always be approaching 1, but it will always be less than 1. So similarly, so you can actually predict the RF value of a dye, because you can assign a random variable to the solvent and then you can just estimate it. Let's say if I had to calculate predict the value of A, so I can predict it to be around 0.6. Okay, so you can also predict the values. So that would be all from the paper chromatography. Yes, that would be all from paper chromatography. Now let's do some past papers related to this chapter quickly to cap this chapter. Okay, question number 1. A fractional distillation apparatus shown is being used to separate a mixture of two liquid. A thermometer is missing from the apparatus. Where should the bulb of thermometer be placed? Always remember, the bulb of the thermometer will always be in front of the opening of the condenser, because from here vapors will enter the condenser. We want to check the temperature over here. If it reaches, for example, in case of water, if it reaches 100 degrees Celsius, we know temperature here is, if temperature here is 100 degrees Celsius, we know that water will start to come here and enter the condenser. So answer would be B. Okay. Question number 2. In fact, question number 2 is from Solve. So it would be better if we do question number 3. Let me zoom out a bit. Okay, the apparatus shown is used to distill a dilute solution of ethanol in water. Right. Which graph shows the change in concentration of the ethanol in the boiling flask as the distillation proceeds? They're asking about the change in concentration of ethanol. The boiling point of ethanol is 78 degrees Celsius. The boiling point of water is 100. So ethanol is going to boil. It's going to enter the condenser. So if they are asking about the change in concentration of ethanol in the boiling flask, this is the boiling flask. So obviously, the concentration of ethanol is going to decrease because it has a lower boiling point. It's going to go into the condenser and it's not going to be here in the boiling flask. So the answer would be what? Between C and D, both have decreasing concentrations. Okay, but here in D, concentration is decreasing first, it's increasing first, and the evidence of that it does not lie in this diagram. So the answer would be C. Okay. Question number 4. I explained this concept a bit during the lesson as well. So, which row explains why fraction R is collected above fraction S? Why R is collected above S? R is, the boiling point of R is higher than S. That is true? No, it's not true. Boiling point of R is not higher than S. It's lower than S. That's why it is going from a higher exit as compared to S. So the A and B are both wrong because boiling points are not higher. R's boiling point is not higher than S. The boiling point of R is lower than S. And so is the mass. The answer would be D. Question number 5. Copper sulfate crystals are separated from sand using the 4 processes listed below. In which order are these processes used? Okay. So we have copper sulfate and we have sand together in solid form. So this is soluble, we know. Sand is insoluble. The first thing we'll do, will dissolve both of these things in water. So copper sulfate will dissolve and sand will not. So we can filter the solution. So sand will be separated and the filtrate would be the copper sulfate solution. So you can do what? You can evaporate it and the crystals will come out of copper sulfate. So the answer would be dissolving, filtering, evaporating and crystallizing. Question number 6. A mixture of 2 substances is spotted onto a piece of chromatography paper. A paper is inserted into the beaker containing a liquid. For separation of substance to occur, the spot of mixture must be placed so that the spot is just below the level of liquid. No, it must be above the level of liquid. Okay, so it cannot be it should be soluble in liquid. That's true, because chromatography's principle hinges on the solubilities of the colored substances in the mixtures. Okay, so क्या करेंगे हम? B. Okay, that's fine. That's fine. Yeah, that's fine. Okay, this statement is correct. Black ink can be made by mixing green, red, and yellow ink. Okay, how do we know that? You have to see the spots that are adjacent to each other. If the spots are adjacent to each other, they are going to have common colored substances. Okay, if they're saying black ink can be made by mixing green, red, and yellow ink, so check black ink. Can it be made by green ink? Yes, it can. What about red? No, red, the one, this spot is not here. Okay, so no. Okay, brown ink can be made by mixing blue and red inks. Brown ink can be made by mixing blue and red inks. So blue, my baby blue. What about red? Blue is there. What about red? Either spot and no, either spot. This spot, red cannot make brown. One of the spot is not there. Yellow ink can be used to make brown ink. Can yellow ink be used to make brown ink? No, no spot is adjacent. Yellow ink may be present in green ink. Yes, yellow ink may be present in green ink. This is the only spot it can be present in green ink. Yes, the answer would be D. Okay, we did this. How is the RF value of the dye calculated? This is the dye. This is the dye to dye for. Okay. Okay, so what would be the answer? Distance traveled by the solute over distance traveled by solvent. Distance traveled by solute is this much. Right? This much. From spot to origin line se measure karna. Have to measure from the origin line. Y over x plus y. The distance traveled by solvent is x plus y. Do not measure from here. That is the original level of solvent. Okay, you have to measure from the spot of dye. A test tube containing a liquid X is placed in a beaker of boiling water. The liquid X starts to boil immediately. What is the boiling point of X? Since it started boiling immediately and test tube containing a liquid X, which means at room temperature that X is a liquid. So it means that its boiling point is above room temperature. Okay, and since it started to boil immediately, its boiling point can be 100. Yes, it can be, but let's look for better answers. Above 100, no, it can't be because it started boiling immediately. Between 0 and room temperature, no, room temperature, because it was liquid at room temperatures cannot be seen. Between room temperature and 100 degrees Celsius, that is true. That is true. Okay. Oh, there are some questions still left. Okay. Substance X melts at 53 degrees Celsius and boils at 100 degrees Celsius. It does not dissolve in water and it does not react with water. Which diagram shows the method most suitable for separating X from a mixture of X and water? So the answer would be, the catch is it does not dissolve in water, so it has to be C. Have to filter it. Yes, see, the thing that I was explaining, they told you the RF value is 0.5. So which one has the RF value 0.5? The 0.5 value will be of the dye, which has traveled exactly half the distance what is traveled by solvent. Okay, solvent will have traveled twice as that of the dye, which is the answer would be, which is why C. Describe and explain how fractional distillation can be used to separate the gases in air. First of all, you'll have to tell them that air has to be liquefied. It will be liquefied by cooling. Liquefied by cooling. Then liquid air will be heated in a fractionating column and various components of the mixture obviously will be separated on the basis of the difference in their boiling points. Will be separated as per their boiling points. Separated in the increasing order of their boiling points, which means that the component with the lower boiling point will evaporate first. Boiling points. Then they will then be condensed and collected. Be condensed and collected. Okay. Draw a label diagram to show the apparatus used in the paper chromatography. You have to show the solvent, the mixture of metal lines. I showed you in the slides as well. Just have to draw this. Make sure that this is your origin. This is the origin line. This is the final solvent position. This is called a chromatogram. This is the solvent. Whenever you write origin line, must be above the level of solvent. Okay. Which of the metal lines are present in the mixture? You can see B. This was the spot of the mixture. B is clearly in the mixture, and E is clearly in the mixture. Calculate RF value of metal line A. So this is drawn to scale, so you can use a scale to measure this, but you can have basic idea about it. It would be around 0.75, just a vague idea. Ammonia can be used as a locating agent for the metal lines. What is a locating agent? Locating agent is used to make invisible spots visible. To make invisible spots visible. Okay. They also ask you about amino acids. Okay. Amino acids are colorless substances, but they are separated with the help of chromatography. They are colorless substances. They are colorless, but they are still separated by chromatography. How? We use a locating agent. Okay. Remember, chromatography is also used to separate amino acids. So whenever you're writing the description for chromatography of an amino acid, do mention the addition of a locating agent. Okay. We did most of the questions. Type of question that you've done. Okay, guys. See you in the next class. Stay tuned. Allah Hafiz.